Now, until recently, pumped hydro was about the only option for large-scale energy storage. That is now changing with the incredible drop in the price of lithium-ion batteries. And so probably batteries are going to be what drives the decarbonisation over at least the next few years. Here is the development of lithium-ion batteries from 1970 through to 2015, and you can see the price has plummeted and the amount of energy per kilogram has gone up, 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 up. And batteries are wonderful in many respects. First of all, they can have both high power and energy ratings. They can store a lot of energy and they can release it very quickly if you need it. They're compact. A lithium-ion battery storing a given amount of power is much smaller than a pumped hydro system storing the same amount of power. And they're scalable. You can have small ones or big ones. You can put them exactly where you need them. Pumped hydro would have to be located in valleys outside, whereas you can put a battery right in your house or right in the town. And they're getting affordable. The price has come way down. It used to be they were so expensive it was only used in real niche applications, but because the price has become so low, that's no longer the case. So you can see over a few years what sorts of storage are being installed. Back in 2011 there were lithium-ion batteries, lead-based batteries, flywheels, flow batteries and so on. But as time has gone on it's spread more and more towards lithium-ion, and the other forms of storage have dwindled, simply because lithium-ion batteries are getting so good and so cheap. Their main competitor for a long time was the lead-acid battery. This is powers a starter motor in most internal combustion engine cars. There are billions of them around the world. And you have either a gel or sulfuric acid electrolyte with lead anode and cathode, which stores the power. But they're not really great for power system applications. They're too expensive and don't store enough power. Lithium-ion batteries, now there are many different types. But basically the energy is stored in the electrodes via interactions of lithium ions. The electrodes are usually graphite and lithium ions store in them, and that stores the energy. You can have liquid electrolytes, though increasingly people are researching on solid state electrolytes. And exactly what electrolytes and what electrodes are used will determine how much power you can store, how cheap it is to build, how lightweight it is, what elements are used, how much power it generates, but they're all pretty good. Another technology which may be a wave of the future but isn't quite there yet, but is very actively being researched, are flow batteries. The idea here is that the energy is stored in electrolytes, two, a positive and a negative one, and these can be stored in large tanks separate from the actual reaction cell which has the electrodes. So the idea is that when you are storing electricity, because the sun is shining and the wind is blowing, you can steadily pump these through and get them ready, and then pump them out all charged up. And if you make these tanks big enough, you can store huge amounts of energy and then pump it back in when you need to supply the energy. So this may be a wave of the future. There are batteries out popping up all around Australia and the world. Here's the big Tesla battery outside Adelaide in South Australia. At the moment, they're usually for very short term. They're used for making sure that the sine wave of AC is reinforced to keep the whole system in sync, and they're used when something cuts out very rapidly, like there's a sudden disaster, a coal-fired power plant trips, a wind power transmission cable is blown over or something like that. These can respond in a tiny fraction of a second, unlike anything else. But as they're becoming cheaper, there are going to be more of them, and they'll actually start particularly shifting the power from the daytime solar peak to the night time. This means we're going to need a lot of lithium-ion batteries, and that's quite apart from all the electric cars that are being built with them and smartphones and everything else that use lithium-ion batteries. A typical lithium-ion battery in an electric vehicle is between 30 and 50% is graphite, the electrode, so you call them lithium-ion, but actually they're mostly graphite. 100 kilowatt lithium-ion battery contains 23 kilograms of lithium, 100 kilograms of nickel, 57 kilograms of manganese, and 40 kilograms of cobalt. All of this means is we're going to need a lot of mines to produce graphite, lithium, nickel, manganese and cobalt over the next few years. Here is the current production in the world, and here's what people estimate we'll need by 2030. So for graphite we'll need to go from 1 million tonnes a year to 5 million tonnes. So we're going to need 5 times more graphite mines. Lithium is supposed to go from 100,000 tons to 900,000 tons, so 9-fold increase in the next few years. Nickel less so because it's used for many other things, and manganese a factor of 2. Cobalt, truly scary, 170,000 to 1.6 million. So huge numbers of new mines are going to be required, though this may change. For example, the current generation lithium-ion batteries don't use cobalt so much. But certainly some sort of minerals are going to be used, and we're going to need a lot of new mines for them. So overall, conclusions. Batteries are becoming so cheap that they will probably dominate firming. Pumped hydro will also help for longer term storage, and maybe some peaking gas in the near term, or maybe hydrogen, we'll talk about that later, can be used for prolonged periods without sun and wind. But this too is probably a solved problem. The prices of these things are low enough now that when combined with extremely cheap solar and wind power, even by the time you factor firming in, renewable energy is still as cheap or cheaper than fossil fuels.